So the idea is that there is this picture. Okay, so there's this picture here that I want to convey that we can, we can use these invariants that I'm going to introduce more, from the beginning today, called L2 Betty numbers, and they allow us to count vortex states in a way that I'm going to explain. Okay, and the idea is the following: that when you want to study, so now we can just think of this as studying a charged particle on a Riemann surface. So the point is that the states, these quantum states, they will localize in pairs of pants in a pair of pants decomposition. So when I told you that there is this formula for the L2 Betty numbers of the compact Riemann surface that are here computed, and they must be counting something. So in a way, they are counting pairs of pants in a pair of pants decomposition, but not just an arbitrary pair of pants decomposition. I have to explain a bit more about that, and then we get a basis for these. So for the degree where you get something which is non-zero, which is degree 1, and they are, so basically the states are trapped by this kind of curve, which is what I call a Pochhammer curve, which is the commutator of two circles. You know, this is a commutator, which is a trivial element in pi1 of the pair of pants, but it will define some non-trivial element in this twisted homology of covers. Okay, so in a way, you can think of this as well. This loop will lift to a simple curve in some cover of the pair of pants. Okay, and this is basically, so you have to do the homology there. So this is basically what comes out. Okay. So we're going to work with so this twisted homology that I defined last time, but in the case where this morphism goes to the H1 of the surface. Okay, so this is a particular case of what I called A, this free abelian group. Okay, so so this is what so we're going to fix alpha mostly to be this one. So we can now restrict to loops that are sort of localized, for example, on a pair of pants and so on, right? Then we have to remember that the corresponding homology of covers is not going to be with respect to the Hurewicz map of the pair of pants. Okay. Okay. So what I said, that it cannot be just an arbitrary pair of pants decomposition. It has to be, so it's I'm going to say what I mean by fashionable. So it's a Pochhammer curve in a fashionable pair of pants. So there is this property called being fashionable. Okay. So so definition. It's just a topological condition. So we say that some Pj in the pair of pants decomposition is fashionable. Yeah. Yes, I think you can wrap up. Yeah. So this is an example of what I'm going to say. So if all its boundary circles are non-trivial elements in H1 of the surface. Okay. So they don't separate. For example, in this pair of pants decomposition, there's a problem here that this circle here separates the surface in two. Okay. So this one is trivial in H1 of sigma. So it means that these two pair of pants, they're not fashionable. Okay. And so we say also that the pair of points decomposition is fashionable if all its pair of points are fashionable. Okay. So there is you can easily prove that any Riemann surface, any Riemann surface will have fashionable pair of points decomposition. So this is some argument by induction, which is easy. Okay, and now there is okay. So gluing principle. Okay, so given fashionable pair of points decomposition. Okay. So the inclusions of the elements so induce isomorphisms for all degree. Well, so here again, I'm taking the Hurewicz cover. Okay. Okay. And now this is something you can show using this kind of exercises of yesterday. Okay. So the proof is just So there is something that you need to show for I equals 1. Okay. So this is an induction argument. Okay. So you start. So it's induction by in the 2g minus 2 plus h, this number. So you start with d equals 1. So d equals 1, you have so there the possibilities are just the pair of pants itself. The sigma is either the pair of pants, but there's nothing to show, or the punctured disk. Okay. And here the pair of pants decomposition is just that. Okay. Okay. So this is this is basically so the statement here is just the exercise E1 of yesterday. Okay. And then and then you do the induction hypothesis, and then this is using this fashionable property, you can show that you have an isomorphism for I equals 1. So for I different from 1, you need to show that both sides vanish. Okay, and this is also something that uses so I different from 1 uses the exercise E2 of yesterday. Okay. Right. Okay, so we're heading to so lemma. So E is fashionable. If and only if the inclusion is injective. The inclusion H1 is injective. Okay. So this is just something you can. It's just not really very hard to show, and then you use this to show this Pohama principle. Okay. So so let's have a pair of pants in a decomposition. And now we take F. Okay, so we have so we have F, which is this commutator of two boundary circles. So F with the commutator of two boundary circles. Okay. So yeah, first of all, you have that so you have an isomorphism. Okay. And then you have that these you have okay, so we have, so this is like this case that we had yesterday where you can get a generator of P, which is cyclic, so H1 of alpha of P, which is cyclic, from the generator here. And then you also have that the composition induces also, so it's injective. Okay. Okay. So yeah, so these this first thing comes from this remark of yesterday. Okay. And the second thing is just the dilemma. Okay. So now, so definition. So now I'm going to give you this picture that I sort of said in the beginning that so there are these special cycles called Pohama curves that trap these L2 Betty numbers. Okay, so well, for now it's just they capture these this twisted homology, but we're going to show that the twisted homology is going to give you the L2 Betty numbers. Okay, so the definition is so P B. So let's be okay, a pair of pants in sigma. Okay, so a Pohama curve in P. It's just a loop. So determining a trivial element, so trivial class in homology. Okay, but inducing an injection. Okay. So in a way, so you can think of this as a curve that is somehow in the kernel of the Hurewicz map, but then it lifts to this Hurewicz cover as a loop, which is non-trivial. Okay. Okay. So summary. Okay. So this basically gives you everything that you want to know about this twisted homology applied to surfaces. Okay, so sigma, so it's sigma be orientable. Okay, genus G. So H boundary components. So H punctures or disks removed. Okay, so now you have a pair of punctures decomposition with inclusions ij. Okay, so inclusions for pair decomposition. Okay, and now choose for each pj Pohama lambda j. Okay, so this is what you saw in the picture. So So this is a pair of pants. It's a disk with two punctures, and it's yeah, this sort of curve that goes like that. Okay. So then you have them. So then there is a map. Okay. So so we know that H1. So each H1 has this this F, which is the so the quotient field of the rational of the group ring. Okay. So this is so you have here 2G minus 2 plus H copies, because this is the number of pair of pants you need to have in a pair-of composition of a surface like that. Okay, so now I'm going to say that you can say that there is an isomorphism to H sigma, which is induced by So first you do you go to so first you go to and then you include that. Okay. Okay. So you have an so you have an so then this is an isomorphism. If and only if the pair of pants composition is fashionable. So all the pair of pants are fashionable. Right? So this is really getting sort of reproducing for you this type of result that I quoted at the beginning, which was the calculation by Atiyah. If you believe that this twisted homology of covers is really giving the L2 numbers. Okay, so so here I don't need vanishing theorems, and so it's a direct calculation, and I can really tell you what are the objects being counted very precisely. Okay? So the L2 numbers, I have not defined them yet, but let me just do it now. Okay, so L2 numbers. And so twisted homology of covers. So so these, when people look at these definitions, this looks a little bit complicated at the beginning because it uses some analysis of these Hilbert spaces associated to discrete groups. So this gets easier when we're dealing with the free Abelian group, which is the only case that I'm going to talk about today. But but there are actually different versions of L2 numbers. The one that is relevant for connects to physics is the analytic definition, which is the one that Atiyah introduced, but there are also very different variants of the definition. Okay, so the general situation is the following. So you start with the complete Riemannian manifold. So in this analytic, in the definition with the analytic flavor, you need the metric. Quite often, these invariants won't depend on the metric. Okay, so so you have a cover. You have it doesn't have to be the universal cover. You have so you have some normal subgroup of the fundamental group, and then you have a cover corresponding to these quotient. So these will be deck transformations in some cover of M. Okay, and so let's call this P. Okay, so this is going to be some cover, and then you define these invariants with respect to the cover. Okay, so one way of defining these is so you look at harmonic forms. in the cover. In degree I, it will be harmonic. So forms on the cover harmonic for the metric that you pull back. Okay. Harmonic and with finite L2 norm. Okay. So this space typically will be so there's going to be many copies of M in this very large space, and then the point is that you have to be very careful about completions in the L2 metric. Okay, so there's this notion of Hilbert n gamma. So I'm going to call this group gamma. Okay, so Hilbert n gamma modules. Oh, I crossed the line. Okay, so there is some algebra, some operator algebra here. So let me maybe just say that first. So everything is going to be based on these analyses over sequences on the group. Okay, so these are sequences. So if the group is infinite, it's an infinite sequence. Then look at sequences with complex coefficients, which are absolutely convergent, and then you have the norm of those, the obvious norm, right? Okay, and then you have this algebra called the group von Neumann algebra. Okay, this is just bounded operators from L2 to L2, which are equivariant. So gamma acts on L2 in the obvious way, right? Okay, and then there's this definition of Hilbert n gamma module is a Hilbert space V for which there is isometry which is equivariant. So it's a V with an action of gamma, which is there is an isometry to this tensor product of a fixed Hilbert space times L2. So it is a product of L2. Okay. So that's thing here. So these H2, these L2 harmonic forms. Okay. So these so there's an isometry So this is how you think about the complete. So you complete really the harmonic forms. So differential forms on the cover with the compact support. Okay. And then you do So this you do the L2 completion, right? So this is so here. The point is that this is going to be the fixed Hilbert space. We do it in this way. So you consider fundamental domain, the action domain, right? And then this is going to be the model Hilbert space. Okay, so there is this screw. So this is the same as L2 functions on L2 of M. Okay, so for example, if you're dealing with the M compact, okay, this is just going to be easier, but you can do this actually for any manifold which has a complete metric. Okay, right. And now for these modules, there's a way of counting. So you might have Hilbert. So these Hilbert. So they are in particular Hilbert spaces, but then you want to consider the dimension theory, which is more interesting than the dimension over C as just complex vector spaces, because then the answer would be always infinite. Okay, so there is this dimension theory, this thing called the von Neumann dimension, which is like it's like the trace of the identity of a subspace. Okay, where I am sort of normalizing by the by the order of the group. Okay, so this is something that would be like the trace of the energy in this sense that there's the trace of the phenomenon algebra itself, which is just for such a bounded operator from L2 to L2, I can just consider the image of the identity and then take the inner product with the identity in the L2 norm of the sequence space. Okay. Okay, so this is the So because everything is equivariant, I am sort of really dividing by the order of the group, if you like. Okay. So so then this is how I define this. So this is a possible definition of L2 numbers that uses this dimension. So this is the phenomenon dimension. So I take the phenomenon dimension of that Hilbert NG module. So So this definition was not the one that was given by Atiyah. So Atiyah said that, well, he wanted to define his L2 numbers like this. So limit. And now he integrates over a fundamental domain in the cover of the trace over over forms of differential forms of the appropriate degree of so this thing here is the Laplace operator on I forms. It's like the trace of a projector to harmonic. This is like so this is an operator that in the limit gives you a projection of the forms to the subspace of harmonic forms. Okay. Right. So the two, you can show that the two definitions are equivalent, but this is sometimes not good enough to do calculations. Sometimes it's better to use alternative definitions of L2 numbers that are given by so formulas of this type. So it's the phenomenon dimension of some Hilbert NG module. Okay, and so there's three main definitions. So the analytic, algebraic, which I'm going to just state just to So the algebraic, for example, is so it's the dimension, phenomenon dimension of so this is equivariant homology with coefficients in NT. So I can understand this in so it's the homology. So this thing here is the homology of the chain complex. So you take the singular chain complex in the cover, and so this is this is a Z gamma module because of the action, and now you extend the coefficients to the phenomenal algebra. Okay, so when the base, so this M is compact, the two definitions are equivalent. So you can compute here, and then you have the result for the analytic L2 numbers. Okay, but this still involves the phenomenon dimension, which is something a bit tricky. And this is why I gave myself the trouble of guiding you through this simpler homology theory of covers. Okay, so this is the situation that so this is one way of understanding the phenomenon algebra. So it's it's an extension of the group algebra like that, where there's some completion here involved. Okay, and there's a square of other rings that are associated to these Hilbert spaces like this. So here you can do something. So you can extend further to get something with a ring which is easier to deal with. Okay, which is this ring of sometimes easier. Okay, so this is this ring of so this is the oral localization. Okay, so it means that you you do so localization with respect to the multiplicative set of non-zero divisors. So you sort of everything that cannot be divided in this ring, you sort of add an inverse. Okay, so this is sometimes called the algebra of affine operators. Okay. So this one is kind of better to deal with. So this is the group algebra. Okay, the group algebra. So the group ring. Okay, and there is here a intermediate ring called the division closure of the group ring. So this is the smallest division closed ring that you can get between this and this one. Okay, so the thing is that you have dimension theory for all of these kind of rings, but this one is the one that I'm interested in. But this one is usually the easiest to compute with. Okay, so so if the group is this A, which is the free abelian group, then you get things that are more familiar. So here you have so in this case, you have here the algebra. So the ring of Laurent polynomials. Okay, and then this is just the quote. So you get the field of rational functions in n variables. So this is certainly, it's a field. So this is just so dimension theory here is just linear algebra over that field. Okay. And now you have the von Neumann algebra and the algebra of affine operators. So in this case, you can use the Fourier transform to understand these two. So these vertical arrows are completions, and these the horizontal are completions, and these are localizations. Okay, so you can use the Fourier transform to understand the von Neumann algebras. So essentially bound operators on the n torus. Okay, so this is taking advantage of the Fourier transform that identifies L2 of gamma with L2 of L2, of Tn. Yeah. So this is just bounded functions acting by multiplication on L2 functions on the torus. Okay, and here you get just the measurable functions. Okay. So anyway, so by the way, this is the complexification of what I called F. Okay, which was also this field, the quote of the group ring of A. Okay, and now this is something which, I worked up with Marcel Books, and people complain that this is something that is not really written up, but everyone knew about. That when you're computing L2 Betti numbers for a free abelian group, this is the same as computing so dimensions over F of the twisted homology. Okay, so here I'm taking so this was the setting that I described before. Okay, so this is this already gives you precisely why everything that I've done with the Pohamas and so on, the purpose composition, justify that in this formula, in this computation by Atiyah, you are counting exactly what I explained. Okay, so maybe you have any questions about this? So So there are these things called L2-Betty numbers, and L2-Betty numbers, I'm just going to show that, well, to argue that this is just interesting for physics. And then you have to compute them. And I have given you many different ways of computing them. I think this technology of the twisted covers is the easiest one. Okay? No questions? No, okay. So now I'm going to tell you about, go back to physics. Okay, so charged supersymmetric particles on surfaces. So before sigma was not necessarily compact, but now I'm taking sigma to be compact, orientable of genus G. Okay, and I'm going to tell you about twisted, if you like, canonical quantization. Okay, of well, it's a quantization in the sense of yeah. So let's see. So basically, this is the same thing as in the lectures by Nicholas Garner. So when he talked about supersymmetric quantum mechanics, okay, on a Kähler manifold. Okay, so this was the case where you can get n equals 4 supersymmetry. Okay, so he said that you can represent this algebra he gave. So with the Dolbeault and operators and the joints and so on. So it's exactly this setting. And then he said, well, we can add this prepotential to make this more interesting. So I'm going to make it more interesting in a different way, which is to couple two flat connections. So couple this particle to flat connections. Okay, this is the idea. I still have a little board here. Okay, so this is maybe, so we have a Hilbert space, which is given by forms of degrees. That degree is has values in Z, but then mod 2, this would be a Z2 degree, And you have we interested mostly in the vacua, right? Which is well, so the ground states, they are given by harmonic forms. Okay, and then you have this pairing, fermions and bosons, which does not need to hold in the ground state. So he explained all of that. Okay, so so now we have we're going to couple U1 connection in bundles over sigma. Okay, so so this is going to be, you need, there's going to be a space of possible choices, which is the space of homomorphisms from pi1, U1. So this is a torus. So you have a torus of choices. Okay. So given a choice, okay, so character, you have you can construct some bundle so over sigma, so a local system, right? But now since this group here is abelian, you can as well replace this pi1 by h1. Okay. And the picture that I have in mind is the following. So now once you choose this psi, you have Hilbert spaces that are, well, indexed by this psi, but I want to consider them all at the same time. Okay. So I do the following. So I know that when you pull back to the cover, so the Hurewicz cover, okay. So the Hilbert spaces for a choice of psi, they're going to be forms valid in this E psi, right? But these forms are going to pull back to functions, right? To functions on the cover. So this is what I want to do. I want to consider these wave, so these sort of local system valued waveforms as just forms, complex valued forms on the cover. Okay, so yeah, so they just yeah, so if this upside is just the pullback, yeah, by the Hurewicz cover. So this is a function on the cover. Sorry, a form on the cover. Okay. But now you run, yeah. So now you run into problems because now you want to consider, of course, the you need to have an inner product. You want to consider, yeah, a norm, and then you have problem with the divergences that you can regularize in different ways. Okay, so one possible way is to do what people do in elementary quantum mechanics, which is to when they deal with the plane waves and so on, right? They deal with the things, yeah. So wave functions which are not L2, they are useful to represent sensible wave functions in terms of wave packets. So this is a possibility. Okay. So there is this, yeah, this technology of, yeah, it's basically, if you like, so how much time do I have? Oh, okay. Right. So yeah, okay. So let's see. So this is certainly a possibility. You do wave packets, and you have basically you're going to do like in a way condensed matter theory, like in a lattice. So physics in a lattice, where the lattice is actually the first homology group of the surface. Okay, so you have things like Bloch forms and things that correspond to plane waves and so on in this setting. So this is a little awkward because you're using this kind of, you're using a basis that is parametrized by a continuum. Okay, and now there's this other possibility, which I think is more interesting, which is to consider better bases that are adapted to this problem, which I call Pohammer bases. Bases for ground states. Okay, so discrete bases for your Hilbert space, which have yeah, which have the advantage that each element of the base has L2 norm, has a finite L2 norm. Okay. Right. So now I think I need the. Where is this person? I think I'd like to show. I'd like to show a slide. Yeah. Okay. So first of all, to make you understand quickly what I'm talking about here, I want to convey the picture of, so what is the Hurewicz cover? It's a question. What is the Hurewicz cover of a pair of pants? Okay. So the one way of trying to solve this is, so the pair of pants, as I said, is just a disk with two disks removed. Okay. And now we can make this simply connected by, for example, cutting here and here. Okay. And now we have to, yeah, get an infinite number of copies of these objects, yeah, and glue, you know, along these cuts in an appropriate way, so that you have, for example, the lift of a Pohammer curve, right, being a closed curve in that construction. Okay. Okay, so thank you. So yeah, so this is where we were. That yeah, you have the Pohammer curve in something like that, which yeah, is these commutative to circles, and now it will, yeah, here you see on the surface when you embed in a fashionable way the pair of pants. Okay, and now this is not working. Oops. One more. Is it me who's doing it? Oh, yeah, okay. Okay, so this is, I mean, if you can convince yourself, this is the answer. So this is a picture of the Hurewicz curve of pair of pants. So this is how you should connect this kind of disk with the two cuts, so copies. So in such a way, so now I'm lifting that Pohama curve that was in the other slide, and it lifts to, yeah, that curve. You can convince yourself that this is true, okay? So, I mean, it's the most convenient way is to put, yeah, so a copy of this guy on a lattice of, well, like one of these honeycomb lattices, really, okay? So on each side, you have a copy, and then you connect the cuts in this way to give rise to this, yeah, it's a fat graph that has, that has this shape, okay? So this is somehow, something similar to graphene, right? Graphene is basically, yeah, because now you're going to have layers of these, in various dimensions, right? So you have, you're going to have copies of pairs of pants, okay? Like these. So let me just continue. So maybe I will, yeah, so how, this is just, yeah, anyway, so, yeah. So maybe you can get rid of the screen now, please, yeah. So this was the picture for the Hurewicz cover. So now the question is, what is the relationship of that cover to the Hurewicz cover of sigma? Okay. So the Hurewicz cover, so what is the Hurewicz cover of sigma? Well, anyway, so yeah, so when you have the inclusion, okay, so now what I'm saying is that suppose you have here the Hurewicz cover, right? And this is the this is the inclusion. So now you pull back. So you pull back, yeah, the Hurewicz. So on P, what is the relationship of this cover and what I've shown? Can we get rid of the screen, please? Can you just pull the screen up? Okay, so the answer is the following. Well, this is going to be what you might expect, but only in the situation where you have a fashionable pair of pants. Okay, so this IP will have many connected components. Many connected components, right? Okay. But exactly in case of a fashionable pair of pants decomposition, we will get that. So will each cover be a copy of the Hurewicz of P, okay, with the quotient. So this cokernel, so H1 sigma P, sorry, sigma Z over the, yeah. Okay, so this is a free group that acts on the set of copies of connected components, right? Okay, so this is the picture of graphene that I was sort of advertising. Okay, and now there is so now there is this idea that you can now have just exactly as I mentioned that you can have harmonic forms representing classes in the RAM cohomology, right? You can also have harmonic forms in the cover, right? In the cover of sigma, in the Hurewicz cover, localized at the, so these copies, so these simple curves that were in the previous picture. Okay, so this is what I call the Pohama states. So Pohama states are wave functions, harmonic forms in yeah. So maybe right. I should. I'm 2 minutes past, but okay. But yeah. Anyway, so right. Okay. So yeah, there's going to be these states which are going to be indexed by a J, which is the label for the pair of pants, and the label that is in H1. Okay. And you get a complete basis, and well, anyway. So this is basically what is kind of the advantage. And now let me go back to vortices. I'm sorry, I really need to tell you something about vortices. Okay. So all of these, so basically, I can do this now for the moduli space of one vortex, which is a copy of sigma, now with the L2 metric, and understand exactly, the one vortex, the quantization of one vortex. Okay. So how about higher vortices? So higher D. So you have now the symmetric product. Well, the first observation is that the pi one of that is again H1 of the surface. Okay. And now you can compute the L2 Betty number. So there's a result, which is the following. Okay. That okay. So in this case, the space is compact, so really the L2 metric does not play any role. So this is going to be a number that does not depend on the metric anyway. But you can do this calculation of Betty numbers and get the following results. So this is the D 0. So this is the I equals D, I different from D. Okay. So let's see what this means. This means that for the D vortex moduli space, you have something which is kind of the higher dimensional analog of these Pohama states, but they are of degree in the middle. So they are in the middle degree, okay, only, okay? And the formula here is very similar to the formula for this generic case, right, for the large area situation in the other type of Kähler quantization, right, which is a formula for, a system of fermions, right, D fermions that can occupy one particle state of which are in a given number. So here the number is 2G minus 2, which was the number that we counted for the one vortex moduli space. Okay. So here this is saying that these quantum vortices are fermions again. Okay. And just one sentence is So by the way, we don't have here a picture of this alternating product, like before, but this is the dimension of the alternating product anyway. Okay. And now just one sentence about nonlinear vortices that I just wanted to mention. The simplest case is what Martin explained in the lecture before. This vortex with target P1, right? In that case, the modular space is not compact, and the fundamental group is going to be something more complicated than a free Billion group, okay? But also not so different from a free Billion group. Okay, so these are called divisor braid groups, and they will govern this kind of picture in situations where the target, for example, is a toric manifold, as in the case of P1. In that case, you have a very interesting situation that I think is very interesting, that the fundamental group is non-abelian, okay? Is a feature. I'm not going to explain what these divisible groups are, but we have presentations for them, and they are kind of extensions of free abelian groups, central extensions of free abelian groups, but nonetheless, there are cases where they are non-abelian. So they can couple to local systems that are not just line bundles, which means that you can start with the gauge theory, which is abelian, which is this case of storic manifold. So Martin was talking about an abelian gauge theory. But then when you go to quantization, you can have non-abelions, okay? You can have bound states, right? That are, given by, not wave functions valued in vector bundles that you cannot reduce to line bundles, okay? So I think this picture is quite interesting. So already the P1 model, which Martin said is, well, you said something about simple, right? Simple and interesting. I agree, it's simple and very, very, very interesting. It already has this picture of non-abelians. Okay. And I think this is a good point to stop. So maybe I should also say, I forgot. So the only thing here which is difficult in this calculation is that we had to use is that is obtaining the homotopy type of the fundamental of the universal cover of the symmetric product. Okay. So can you understand the topology of that? So the topology of this is already something that says that there is something special about this kind of middle degree. Okay, and this is this result involves that calculation. So HI, so yeah, HI of these, the single homology.